So thank you very much for joining us for this quick EM server webinar. I'm Daisuke Kihara, the PI of this project, cryo-EM structure modeling tool development, and we have today Junhong Park and Genki Terashi who are following after my presentation. So today we will briefly go through this structure modeling servers methods implemented to this EM suite server. And the focus is two methods. Among these several tools, we focus on this DAQ-Score. This is the structural validation score, which is very useful to check if your protein structure model fit well to the supported by the density or not. And then we also describe the CryoZeta. This is our latest structure modeling methods for protein and DNA RNA complexes using the very advanced deep learning methods. So this tool, all of this tool are also available as a source code. We have a GitHub page, and then you can download it. But this server will give you a quick access and the easy use of these tools. So we have those. There are many tools right now. So those include protein structure modeling tools for proteins, DNA, or complexes, including the CryoZeta, what I'm going to describe, and then structure validation tools and the refinement tool, and then more classical structure fitting tools, VESPR, and secondary structure detection tools. So then I switch to my slides. Okay. So this is about the server. Now, all right. As you know that cryo-EM, information you can get, structure information you can get from cryo-EM data really depends on the resolution, global resolution. Here, I'm showing the very high resolution map, 1.92 angstrom globally, 3 angstrom, 6.5, 8, and further down to 16 angstrom. And since the resolution really determines how much you can see from the map, we have been developing several different tools that fit to the basically two ranges of the resolutions. Using deep learning, up to about 5 angstrom, you can detect amino acid position or side chain atoms, and also the residue types, because you can see the side chain atoms by deep learning. We can also detect amino acid types or also the ligand. And then up to around 10 angstrom, we can see the secondary structures and part of the main chains. Then following that, up to 2 angstrom, you can use conventional tools for modeling. Following that, we have been developing two types of methods. Up to 5 angstrom, we have been developing the tracing method and atomic detail structure modeling methods, including protein modeling tool, deep main mass cryo-read. Today we skip this earlier work and then focus on this CryoZeta. We are also working on ligand detection methods, which hopefully we can present it next time. And then the DAQ quality assessment score. We can, by using the amino acid detection method, we can also see how well amino acids in your model is supported by local density patterns. Although we don't cover it today, up to 10 angstrom, we can do the secondary structure detection of structure fitting. And that is also the powerful methods for structure modeling. Those are all implemented in the EM server. But today we focus on DAQ quality assessment score, because we have now ChimeraX plugin, which gives you the interactive assessment of the model, and then new methods CryoZeta. So I first talk about the concept of the and approaches of DAQ score. So here, actually, we have been examining, checking the PDB entries from cryo-EM for now a couple of years. Every month we are checking the structures in PDB from cryo-EM. And then actually about 15%, we found that about 15% of the models have some errors. Typically, it's a shifting error. And then here I'm showing some examples. In this first example, those in the middle region, which is actually, as I show you later, flagged in red by the DAQ score, um, has has proline and phenylalanine in this density, and actually proline is fitting to this density, but if you shift the sequence by, well, 2 positions, if proline goes to here, which originally occupied by phenylalanine, actually everything fits much better. So in this case, there are a residue shift of 2 residues. C alpha positions are okay, but residues are shifting by two residues. Here, similar story in this example. We have isoleucine, 2 isoleucines here. Well, this side chain is a little bit off, well, outside of the density, but everything fits nicely if you shift further. If you shift the 6 and isoleucines 6 and 5 lower, then put phenylalanine 8 here, serine 7 here, then everything fits better. And these kind of errors are not easy to detect by eyes, and also the, well, Q-score, because in terms of density, they overlap quite well. And so, well, beyond the volume overlap, if you use deep learning, we can see if the residue positions are fitting well or not. In the last example, this is an extreme example. Even like as chains are almost entangled, which doesn't look like protein, but those sometimes extreme examples are observed in PDB. So now, okay, so we developed the methods called DAQ score. And I just briefly explained the concept of DAQ score and show you how it works. So in the DAQ score, so you have a protein density, protein model fit to the density, and then what DAQ score does is to compute the probability that each amino acid exist, locate at each position. So for example, if you have so here we have 3 scores, and then let me explain these 2 scores. This is amino acid similarity, amino acid score, AA score. In this AA score, what it computes is, suppose the residue position I in your model is tryptophan. It first computes the probability that tryptophan at that position by deep learning. And then that probability value of tryptophan at that position is normalized by tryptophan probability of basically from all the maps. Then take a log of it. So if tryptophan at that position has higher probability than tryptophan from everywhere, background, then this fraction is larger than 1, and if you take a log of it, you have a positive score. So positive DAQ amino acid score tells you that amino acid at that position is at least better supported than of that amino acid type than overall background. Same thing about atom score. This atom score tells you the probability that, C alpha position located at that position in your model relative to the overall C alpha probability of the map. So positive means that at least C alpha position at that place is supported better than overall background. We also have a secondary structure score, but the idea is the same. Now here is the overall distribution. We checked this is a distribution of amino acid residues, which are, we believe, wrongly placed in red, and then probably correctly placed. Here in red, if the residues are placed in a wrong place, it shifted. That overall score distribution goes to negative mostly. And the blue is the one which, the authors of the PDB entry, didn't think they're wrong. So if you look at the cutoff value, if the score of DAQ score is less than minus 0.5, almost 100% of the cases, they are wrong. So we use DAQ score of minus 0.5 as a cutoff value to say that highly probable wrong amino acid assignment. So, okay, so this is a score distribution, and then this is some examples of how the DAQ C alpha position score and the amino acid score look like. This is an example that the DAQ's C alpha score is positive, which is good, and then DAQ amino acid score goes to negative. These alpha helical regions have this score range, and which is shown in the plot here. Amino acid score is in blue, C alpha score is in red, orange. So in this case, since C alpha score is positive, that means that amino acid score itself, helix is helix. This is correct. We believe this is correct. But the amino acid assignment is wrong in this region, in this helical region. And if you shift it, then everything goes to positive. This is at the after shifting. Blue is after shifting. The red is in PDB. This is the opposite situation. Now here, DAQ C alpha score is minus 0.5, negative, shown in the upper plot, but amino acid score is positive. In this case, actually, there was a small shift of the structure, rigid structure shift. Since it is a small shift, DAQ C alpha score goes negative, but amino acid score is within that amino acid range, and that's why it is positive. And if we shift it by rigid shift, then everything goes to positive. So C alpha score and amino acid score have those different roles. C alpha tell you if the C alpha positions are correct, overall conformation is correct. Amino acid score tells you possibility of residue shifts. And we would encourage you to include the DAQ analysis in your publication also, because Q-score tells you if the atoms are resolved for your resolution of the map, but the DAQ tell you that residue shift is not happening or happening. And so those DAQ score and Q score have different roles. We also have a DAQ score database. We are updating it every month, and you can see the DAQ score analysis of the existing PDB entries. Now, DAQ score is also included in the PDBJ, Japanese branch in PDB. So you can also see it in PDBJ website. So now DAQ is also released as a plugin in ChimeraX. That is very useful because while you are shifting the residues, you can dynamically see the change of the scores. So that will be explained by Genki Terashi later. Now, all right. So next, I explained the CryoZeta algorithms of CryoZeta a bit. So this is the latest the structure modeling tool from us. What it does is it is really like an integrated deep learning pipeline of protein and then DNA, RNA structure modeling. So this is using the deep learning, almost end-to-end deep learning methods, and it is inspired by the AlphaFold 3. So as you may know that AlphaFold 3 is an upgraded version of AlphaFold 2. And in AlphaFold 3, you can model protein and DNA, RNA, and ligand complexes. Now we use that architecture, that architecture, but now including the cryo-EM information directly to the density map. So the input of this CryoZeta is protein and DNA, RNA sequences, and then cryo-EM map. From cryo-EM map, first we apply the deep learning methods to identify atom positions, and then that goes to the deep learning methods, and then there is a tension between the identified position, atom position in the cryo-EM map against the amino acid in the sequence, and then that conditions are put into the diffusion model, which generate the structure. So in short, CryoZeta is really a fully integrated protein, the macromolecular structure modeling deep learning methods with under the condition of the density map. Well, this is some our comparison. This is comparing our methods on y-axis relative to other methods, and the performance is really good compared to even by against our earlier methods. DMM is deep mass. This is our earlier methods. Compared to those methods, CryoZeta really performs much better than in many resolution range. It can do the, so this is a direct comparison between the CryoZeta with AlphaFold 3. AlphaFold 3 in large complexes often, predict individual pieces correctly, but forms more compact structures like this. But in CryoZeta doesn't do that because CryoZeta understands the density positions. This is an example of protein, DNA, RNA complexes compared to AlphaFold 3 or model Angelo. Since AlphaFold CryoZeta understand where the RNA or DNA locates in the density, it does a better job than, of course, AlphaFold 3. Okay, so that's all I have. And then I'll now pass it to Junhon, who will briefly explain the website.
Yes. Hello, everyone. My name is Junhong Park, and I'm excited to introduce the EM server to you guys. In this presentation, I'll go over what you can do with the server and how to fully utilize the EM server. So EM server can be accessed at dem.KiharaLab.org. The platform is built for the principle of providing easy and accurate structure modeling and validation for cryo-EM maps. Currently, we're hosting 16 different algorithms for different purposes developed by our lab. These tools can cover from like structure modeling and validation to the refinement, just like the professor mentioned before. We're hosting this web server for about 2 to 3 years, and we supported almost over 8,900 jobs from more than 1,900 users worldwide. So now let's start with how to use the server. You can submit the jobs without making an account, but we highly recommend creating an account because you can get much more benefits from it. If you make an account, you can easily track your past jobs, and then the communications between the developers can be much easier. So now, after creating an account, you can submit a job. The first thing you need to do is choosing the right algorithm. As I mentioned earlier, we have 16 different algorithms for different purposes for both protein, DNA, RNA, and protein DNA complex with different resolution ranges. So please check all these algorithms and decide which one will be the best one for your task. Next, you need to provide the input files. For example, DAQ-Score, you need to provide two inputs. First one is protein structures in PDV format, and the second one is cryo-EM map in MRC or MAP file. And then after uploading these two files, you can click the upload button at the bottom, and you can successfully submit the job. After submitting the job, and the job is done, you can see the 3D visualization in the job result page. Um, yeah, you can always revisit the past jobs. In the job manager page, you can track all your past jobs and their status. You can also filter these jobs by their status, such as like success, fail, running, or by the algorithms and the date. Um, What truly sets the EM server apart is that the manual review system. If a job fails or the output doesn't look right, you can describe the issue in this problem description section and click the Submit for Review button. Then the developers will manually check your job and then give a personal feedback to you through the emails. Even if you don't request it, the developers will go through all the failed jobs and then give personal feedback to you. Um, for example, we handle from like very simple formatting errors, like white spacing in the file format, or we can provide some detailed scientific feedback, such as notifying you that if our deep learning methods fail to detect DNA or RNA, so that the output structure doesn't exist. The kind of feedback we provide. So if you have any issues while you're using the server, just please use this job review functionality. We want the EM server to be more than just a collection of algorithms. We want it to support, we want to make it as a supported ecosystems for structural biology research. So if you have any questions or run into any issues, just please don't hesitate to reach out to our team. Thank you so much. And Genki will continue to the explanation of the DAQ-Score plugin and then CryoZeta.
Okay. So, hi everyone. My name is Genki Terashi. I'm assistant research scientist in the KiharaLab laboratories. Let me share screen. Okay, so in my part, I will explain how to use our tools, so DAQ plugins and CryoZetas. So DAQ plugin is a real-time model evaluation method, and also it provides the correction guidance. So from density map using the deep learning method, they make the pre-computed DAQ score grid. Then user can modify the structures. Based on the structure, DAQ plugin show the accuracy of the modeling. So CryoZeta, as Professor Kihara explained, this is an accurate molecular structure complex modeling method. So it can handle the protein sequence and also DNA, RNA structure with a cryo map. It can provide the very accurate complex structure model. I'll explain how to use these tools. Okay, so first of all, DAQ plugins is currently available in the ChimeraX. So if you have a ChimeraX, please go to the toolbar here, then click here, then you can click the more tools. So ChimeraX provides the plugin website. It's categorized to the different categories. Then please click the validation categories. Then it will show the DAQ plugin here. And just click, then click the install buttons. That's it. So you don't have to install any environment and GPU card. Just click the buttons. Then ChimeraX handles everything. Then once you install the DAQ plugins, you can start this plugin in the ChimeraX. Again, from the tools, click the validation. This is the category. Then DAQ plugin. Then once you click these buttons, then this GUI will pop up. Then to compute the DAQ score, so there are two steps. First, you need to compute pre-compute the DAQ score on grid. So it use the CPU, only CPU, but it's very fast, quick, so it takes only 1 minute. Then search entire density map, then compute the DAQ score on grid. So here, so I specify the structure, PDB structure, the number 2. Then this is the ID for the density map. Then also I specify the file of the intermediate file. So this computation is only required only one map for once. So if you already computed this grid data, you can load from here. Then click this compute DAQ score. After you clicked, it will show the molecules with the DAQ score. So then the step 2 is the real-time scoring. So DAQ plugin provides real-time scoring. So just click the Start Live Update. For example, this is a density map and structure. But once you click the Start Live Update, then it shows the DAQ score colored. Also, you can edit the structures. So here, so I shifted the PDB structure relative to the density map. Then this plugin immediately update the score. So here, the protein structure is coming off. Then DAQ score says red. It's a negative DAQ score. It's not accurate. But once it fitted to the density map, it shows a blue positive DAQ score. This is a function for the live update monitoring. And also this DAQ plugin provides the sequence residue shift suggestions. So once we detected the low DAQ score regions, then this plugin tells us which directions the sequence registration should be shifted. For example, here there's a red low DAQ score region. Then click the show arrow buttons. They will show the directions. Okay. I'll start a movie. Then using this shift direction informations, so it can also provide the position constraint information for the isolate. Isolate is a molecular dynamic structure refinement method. So this DAQ plugin automatically provides the position constraints. Then just clicking the add constraint buttons, then run the isolate. It automatically isolate handles the molecular dynamic simulations and shift this structure. Then after using this shift informations, then DAQ score is also real-time computed. So then it shows the blue structures. So initially its red regions are improved to the positive DAQ score. Another function is that in the top, there's a residue table. So user can easily identify which residues, which regions have a low DAQ score. So from these tables, you can just click these columns, then ChimeraX show the low DAQ score regions immediately. Okay, this is a brief explanation of how to use the DAQ plugins. Then I will demonstrate the actual examples. So here I already downloaded the 31563s and 7FET PDB. It's colored by chain. Then click here to validation, then DAQplugin. So this is the GUI. Then I want to evaluate this PDB structure, 7FET. I want to use this map. Then you can specify the output file. For example, I want to make the file name is test demo numpy file. Save. Then click here, calculate DAQ-Score. Click here. Then now it's computing the DAQ-Score among all grid points. So here we can see the progress. It will take less than 1 minute. The number of grid points is 62,000 grid points. So this computation is required only once per map. Once you computed this grid data, you don't have to compute again. You can reuse that grid information. Okay, it's almost done. Okay, so now the protein structure is colored by DAQs. So we can see that these beta hairpin regions have a low DAQ-Score. And also you can click here, shift arrows. It provides that. So these regions need to be shifted to residues. Yep. Then from residue table, so you can easily check the low DAQ-Score regions. For example, here, click here, let's jump to low DAQ-Score positions. Then you can highlight side chain and density map. Yes, so this side chain is coming outside of the density, is not fitted well. The DAQ-Score says this sequence assignment is not correct. Okay, so this is a DAQ-Score plugin. And let's move on to the next part. Okay, CryoZeta. So CryoZeta is an accurate molecular complex modeling tools for cryo-EMs. So we release the programs on our website, web server. So please go to the EM KiharaLab.org, then click the algorithm, then select the CryoZeta. Then once you click the link, the job submission page will be shown. So this job submission page is very easy to use. You just need to provide density map and sequence data. So because the CryoZeta can handle the protein, DNA, RNA, you can just upload the files. Then currently the copy and paste function is not available, but this function is coming in the next update. Okay, then I'll demonstrate how to submit a job. So this is our EM server website. Then click here, algorithm, then CryoZeta. This is a job submission page. Then here, I submit, upload the files. This is one of the examples in the test dataset. So in this job submission page, you can visualize the input density map. But here, this control level shows a lot of noisy data, noisy density. Then here you can adjust the control level. Okay, so for this, I select 0.25. Yeah, it shows the DNA shape here and the protein shape in the middle. Then also the user need to provide the resolutions, but this number is a approximate number is fine. So this time I put 3.0. Here, I will submit the protein sequence, FASTA format, protein sequence, and also DNA sequence, and RNA sequence. Then click the upload button. Then now it's scheduled. So once you submit the jobs, you can check the status of my current job. So for example, here, I already submit a lot of jobs. Then this is my previous jobs. So if you have registered the EM server, you can always, anytime you can check the progress of the job submitted jobs. Okay. Then also I can show the result page. So actually, I already submitted the same job yesterday. This is the result. So it showed a very nice double-strand DNA structures and protein structure here, and also the RNA structure here. So CryoZeta accurately predicts the protein, DNA, RNA, and also the interaction between the RNA sequence and DNA structure. Okay. Yes, yeah, we saw that, these examples. So I also compare with the deposit PDB structures, 9-MTY. So 9-MTY showed us the DNA structure as a purple, magenta, the RNA structure is orange. So it's quite similar with our predictions, CryoZeta models. It can accurately predict the DNA, RNA interactions and protein DNA interactions. So yesterday, I also learned, use the AlphaFold3 server. So AlphaFold3 shows a very nice protein structure, fold, but interestingly, it couldn't generate the accurate DNA structure. So the DNA is a double-strand helical structure, but it couldn't predict the accurate DNA-RNA complex interaction. So our advantage is that we can predict the accurate DNA-RNA protein structure complex using the density information. Okay, so I briefly explained how to use the DAQ-Plugin and CryoZeta. So DAQ-Plugin is a real-time model evaluation method, and also it provides collection guidance. So currently, the DAQ-Plugin is available in our server. DAQ-Score itself is available on our server, but also we newly released the ChimeraX plugins. So we recommend to use these plugins. Then you can learn the DAQ-Score on your laptop. We also released the source code. So if you are interested in it, please visit this plugin. So CryoZeta, so we demonstrated how to use our server, CryoZeta server. So it is a very accurate macromolecular complex structure modeling. Of course, source code is available on the GitHub page. So if you want to learn the CryoZeta on your computer, please visit this GitHub page. Okay, that's it in my side. Thank you for your attention. Then if you have any questions, please ask.
Okay, so okay, yeah, thank you. I created model with my 8 angstrom resolution map as CryoZeta. Now, how I can validate? I see. Okay, that's a good question. Good question. Well, so DAQ validation is designed to validate up to 5 angstrom because the deep learning method used for DAQ was trained on the map up to 5 angstrom. So but it is so well for 8 angstrom resolution. I'm not sure how well DAQ can evaluate it, but please try. First of all, the DAQ is only for proteins. DNA and RNA region will not be validated by DAQ. But this 8 angstrom, this 8 angstrom is a global resolution, and if some part of the resolution, maybe a core of the map, is in a locally higher resolution, DAQ may be able to tell you the meaningful score. So please try the DAQ. Well, let's see how well, and let us know how it works. We are happy to tell you, well, assist you. So one good thing about DAQ is that if DAQ is not confident about the evaluation, if DAQ, deep learning, cannot see much, the score goes to close to 0, telling that there's not, the deep learning is not confident to say positive or negative. It goes to 0. This is also a bit different from Q-score. The lower resolution does not make the score lower. It just goes to 0 to show that deep learning is not confident to make the decision actually. So I think it's worthwhile to try DAQ still. Okay, so another question, could we use CryoZeta for modeling protein DNA or protein only? Yeah, you can use for both. It can work. CryoZeta will work for protein modeling only, protein only modeling, DNA only modeling, or RNA only modeling, or the complex. These are the tools freely available to use. So for academia, yes. For industry, please contact us. For the web server, I think if you're happy to use web server, we are fine for you to use web server even for industry users. Okay, so next one is results from CryoZeta biased by existing PDB models of same or similar complexes. Okay, that's a good question. Yeah, it's possible because so the CryoZeta is trained on the PDB entries from built by cryo-EM map, and it is possible that the model is learning. Well, model is definitely learning patterns from PDB, but as you can, or as you saw in some examples, actually this CryoZeta is really following the density positions, the identified atom position in the density. So it's not like AlphaFold 2, AlphaFold 3. It's not just copying the sequence structure pattern of PDB. It's more like following the map information. But still, it is learned from the cryo-EM map and the PDB. So I cannot say that it's completely free from the bias from the existing PDB, but it's following the map. And okay, so then yeah, how is the data confidentiality handled? Right. Yeah, that's a good question. Actually, if you submit your jobs to the website, web server, yeah, we can see them. We can see what you have input. And in that way, actually, we do troubleshooting for cases where the error happens. So for web server, although we are not checking, well, because we have 10 to 20 submissions at least per day, we are not checking everything, but we have access to your file. So if you have if you want well secure confidentiality, then well, you can download the program source code and then run it locally. And for some cases, for some methods, probably not all of them, are also implemented in Google Colab Notebook. In that case, if you use Google Colab Notebook implementation, we have no access, and if we and then you can well secure the confidentiality against us, but the Google people can see it if they want. So most secure way is to download the code. All right. Any other questions? So yeah, thank you for joining us today. And we are okay. How is CryoZeta different from previous models? Okay, that's a good question. So we have earlier methods, deep main-must. Deep main-must is also a protein structure modeling tool using deep learning. So what CryoZeta is new. A new thing about CryoZeta is it is it is well integrated in AlphaFold 3 neural network architecture. Basically, well, we are not using AlphaFold 3 code due to the license issue, but well, from technical level, it is implementing adding the deep learning information directly to the neural network. So it is doing the structure prediction or modeling under the condition of the cryo-EM information. In contrast, our earlier methods, and then CryoZeta can also do protein, DNA, RNA complex modeling, just like AlphaFold 3 can do. In contrast, our earlier method, deep main-must, or some other methods, related methods by other people, adding the AlphaFold information as a kind of like a structure fragment information. But it's not fully integrated in the deep learning neural network. Oh, okay. So yeah, how does CryoZeta validation compare to DAQ-Score? All right. Okay. So actually, CryoZeta and then DAQ-Score are very two different things. Sorry if we didn't make it really clear. CryoZeta is structure modeling tool. It does not do the validation. For CryoZeta, you have a cryo-EM map and then protein sequence or DNA RNA sequence, and then we do the structure modeling for your protein and DNA RNA within your density map. CryoZeta is a structure modeling tool. DAQ-Score, in contrast, is a validation tool. So it will check, DAQ-Score will check if your protein model fit well to your density or not. So for DAQ-Score, you need to provide your structure, protein structure, and then density map. And then we will check how well they agree. So actually, after you do the modeling with CryoZeta, it's good to run DAQ-Score to confirm that CryoZeta is doing good job in the modeling. Okay. All right. So we are communicating with users very actually actively. So if you have any like problems or questions about our tools, please feel free to email us, or you can also text us on the comment box from the server. And if there is something beyond what server can do, we also have a multiple collaboration with structural biologists. So we can also do the do the modeling specifically for your density map. And so please feel free to contact us. All right. Okay. So then I think we will conclude this webinar. We are planning to do this webinar maybe later this year again. So if you have any request of the tools or something we can develop, also feel free to let us know. All right. Okay. Yeah. Thank you very much for spending time with us. Have a great rest of the day. Thank you very much.